Good evening, all. Welcome to week 12 of the live sessions for optimization from fundamentals. We'll wait for a couple of more minutes to for a few more students to join, and then we'll get started. So the last week of the course essentially focuses on dynamic optimization problems. So we'll briefly cover the topics on basic introduction of dynamic optimization, and then we introduce the concept of policy, what a policy is, why we need a policy, and then we will see the principle of optimality, and then the dynamic programming equation for inventory control problem. Finally, we will reduce the case for a linear quadratic problem, in which case we have the Riccati equation, and then we will take very simple problem, very similar to the one that you have in this week's assignment, so that it can help you solve your assignment problems. So just to start with a quick introduction of what we are trying to do in this lecture is on first one is on what exactly is the dynamic optimization. Till now we have seen problems where we have say we want to minimize f of x by changing this decision variable x such that you have certain constraints that x has to satisfy, which is given in terms of my feasible domain S. So this is what we were trying to do up until now. But even in dynamic optimization is going to be something similar, but the only difference is the x here that we are saying is kind of each x will depend on every other x. So for example, if f is represented as f of x comma y and so on, the value at this the value of this y will also depend on the value of x that you are choosing. So it won't be a straightforward problem. So how do we control that? How do we change that or transform that into a problem that we can actually solve is something that we do in this dynamic optimization problem. And you can also see that from the name, the way we named it, the dynamic optimization. The example for this is an inventory control problem. So for example, if you're imagining a shopkeeper who kind of monitors his stock continuously, and then depending on the availability of the stock in his shop, he'll decide when to order and how much to order. So the problem now is the how much to order and when to order. These are the two questions that he needs to answer. So, or if you want to put it in a simplifier, all you need to know is that every time instant, you know that you can order every day. So each day at a given point of time, what is the amount of quantity that he needs to order? Is a question that he needs to answer, and that is what we are trying to solve in this inventory control problem. And the main challenge here is we do not know the demand that we are going to have in the future at the time when we are making the decision. That is the main challenge in this problem, in dynamic optimization problems. So changing and often unknown demands with the minimal cost. So we want to minimize our total cost, where this total cost will essentially include two costs. One is the inventory cost, or inventory cost, or basically let me call it holding cost and purchasing cost. Holding cost is basically say the rent you have to pay for the particular shop you are owning to hold those particular items, or it can also be the amount of money you are paying for holding that particular stock at your place instead of selling it. It can also include something like some items which are perishable items. So if those items expire or something, then you also have to incur the cost of that. That those things are actually coming under the holding cost. And then comes the purchasing cost, is basically if you decide to order some quantity, then you have to pay some money to get that quantity, and that is your basically a purchasing cost. So these are the main two types of costs. So we do not want to buy everything before and keep them in stock, because our holding charges will keep increasing, and and since we do not know that the actual demand before, we cannot even decide how much to actually purchase. So in these kind of scenarios, what is optimal strategy that we have to do? So the first step is anyways deciding what the decision variables are, and then how do we formulate the objective problem in a mathematical way. So the notation that we're going to use, or which has been used in lecture videos, is we define the xk as the stock available at the beginning of the kth period. So our decision horizon is divided into some periods. So these are my end decision horizons, and then I'll eventually reach. So xk is basically at this kth period. So this is the 0th period, first period, second period, and so on. At this kth period, what is the stock that is available with me is my xk. And at this xk, I do not know what is the demand I'm going to have between k to k plus 1 period. So that is my wk. But I have to order at this time instant. That is my uk. What I'm ordering at this time instant is uk. Xk is the current stock available. So using these three information, I can calculate what is the value of stock at time k plus 1, which is simply xk plus 1 is xk plus uk minus wk. And our objective is to find this uk for all values of k given this particular transition equation. So this is basically how your stock is going to update depending on the decisions you are making. And then what is our object? Maybe I should say our aim is to find uk. And what is our objective? Our objective is to minimize the cost. So my decision variables I have chosen here are uk. So then comes the problem of so what happens if I have to choose uk? For example, at every point I can decide. For example, I can decide certain lots. So there are three possible combinations that I can actually have. Hi, good evening. Yeah. So what I was trying to say, so we can actually get this value of uk that we have to choose at every time instant. So instead of solving for uk at every time instant, what we are trying to do is formulate this uk as a function of xk, so that you as a shopkeeper will see, okay, if this much stock is available with me at this point of time, I have to order this much on this particular day. So that you don't actually explicitly solve for uk, but then you come up with a strategy, and that this process is called optimizing a policy. So where uk is formulated as a function of xk, and your objective is to determine this function mu. So now we are changed the problem from solving for u to solving for mu. And in this case, the optimization function will become like this, where you have to minimize the total expected cost, where this is the residual cost that you're going to have, like after n time periods, say for example, after 1 week or 1 month, whatever it is, what is uh, the leftover? That leftover, whatever is there, you cannot sell. So that is the residual cost that you have. And this R of xk is basically at that time instant, what is the holding cost. And if you decide to order uk, then you have some purchasing cost as well. And why are we keeping this expected? Is because we do not know the demand beforehand. So we have to assume some kind of demand is some kind of a random variable. And once it becomes a random variable, this entire the quantity xk plus 1. So I've written xk plus 1 as uk minus my demand, and this is a random variable. If this is a random variable, then xk plus 1 is also a random variable. Even though I know xk and uk, even if I decide a value for uk based on uk is now basically mu k of xk, even this mu k is a deterministic function, even though I know the xk which is also deterministic, but because this demand is an unknown random variable, xk plus 1 is going to be a random variable. So if one step becomes random thing, then the entire thing, the entire process to from 0 to n minus 1, everything will become random. So I cannot get an actual cost, I can only get an expected cost, essentially, which means I'll have all possibilities with certain probabilities associated with each cost. So that's where this expectation comes. And this set of functions mu k, mu 0 to mu n minus 1 is called the policy. And what we are trying to do is find this policy such that it will minimize the cost associated with it. So all we know for sure is x naught, because the x naught is at the initial state. Once we know the initial state, depending on the uk values, you can emerge into different possible combinations of x1, x2, and all these values. So all that matters is this initial state itself. You can also think of this as solving a ODE, where you have time governing equation, something like say dt equals to some q of t, plus some w of t, where this is basically my, if you kind of apply your finite difference or something, so this becomes tt plus 1 minus tt, if the delta t equals to 1, tt plus qt plus w of t. So this is basically a first order differential equation that we are trying to solve. And in order to solve this, all we need to know is the initial condition, like this specified along with the t at t equal to 0. When you combine both of this, then the problem is completely defined. So in a similar way, here we need to know the initial state, and depending on the initial state, what we are trying to find is this q of t. This q of t is basically my u here. This that is what we are trying to find. And eventually, once you get u, you will also know what are the intermediate states. Like, you know, if you know the q, you know this equation, so you can always substitute, use some random number generator, get this w, substitute that here, and then get tt plus 1 based on t0. So from t0 you'll get t1, use t1 to get t2, t3, and so on, and till whatever time origin you want to calculate, you can calculate that. But obviously you can see the problem here, that we have only one equation and then we have two unknowns. That is, here we know t0. For example, if you want to solve for t1 or t2, I do not know q, and I do not know the previous value of t as well. So then that's exactly where the optimization is coming. So there could be 100 different strategies, but what we are trying to do is find that strategy that will minimize the total cost. That is this j pi, and that cost is essentially includes this r of xk, c of uk, these functions as well. So for that, we need to know how much weightage I have to give for keeping the current value of t as well as for updating the value of t. So we will solve one problem on this so that it becomes clear. The next concept is the principle of optimality. So the statement goes like this, but you can also think of it in a very simple way or intuitive way, where if you want to move from some particular point A to B, there could be different paths to move from A to B. For example, if you want to try to minimize the total length of the path that you are traveling, then this is the solution. And if you know that a point C lies on this particular point, then in order to move from C to B, also this is the only possible minimum way that you can use. So as long as this path AB is the minimum path from A to B, and if C lies on that path, then C to B, this is also the minimum path, because any other path that you try will eventually be longer than this one. Any other path that you choose will actually be longer than this one. That is what it states. And when will this hold is basically, we will see that in the next derivation as well. So this thing is extrapolated into the cost function as well. So what we are trying to say here is the cost at the kth time step. So if you have gone through the lecture videos, you might have already been familiar with this idea, that what we are trying to do is we were not able to solve the problem in the forward sense. So if you start with x0, then you go to x1, and so on till you reach xn. This is what we have to do ideally. But then if you start from x0, you can have, say, for example, two different combinations of x1. And then for each combination, you can have two more different combinations of x2. So this keeps growing exponentially. So we were not able to solve in this forward sense. So what we were trying to do is, in deep dynamic programming, is solve from the backwards. So you find an optimal value of xn, use that value to get xn minus 1, and so on till you reach x0. So since we know that if the best possible path from it, like if I break the path anywhere in between, and this will be the optimal path, using principle of optimality, I can say that if I connect from this to, if I add one more step, then that will also be optimal. So this is like your greedy search method. So at each and every step, you only choose the one that will kind of minimize your total cost. So take only steps that will minimize your total cost at that particular step, but in a backward way. Instead of going in a forward direction, you'll be going in the backward direction. To put the same thing mathematically, what we are saying is the cost at the kth step is jk of xk, is basically whatever the holding cost plus the ordering cost. And then you also need to take into account, because at kth step, whatever you're doing, you will go to k plus 1, and from k plus 1, you will have to spend some extra effort. For example, if you are at kth step and you want to go to k plus 1 step, here the cost is jk. So whatever this cost is basically includes the entire cost for whatever decisions you are going to take at kth step and whatever decisions you are going to take at k plus 1 step. So what we are doing is, at kth step, my decision includes r of xk, the holding cost, plus c of uk is basically the cost that you have to incur for purchasing. Plus, you once you do this plus this, you will be at the k plus 1 step. So at k plus 1 step, whatever decision you have to take should be such that you will minimize the cost at k plus 1 step. So the cost at k plus 1 step is jk plus 1 into xk plus 1. This entire thing is basically xk plus 1. So this kind of formulation will ensure that you can recursively solve these equations. So you solve for Jn and then use that equation in this. Once you have the Jn, you put that here. Then you can solve for Jn minus 1. And then you can solve for Jn minus 2 and so on. The derivation is there in the lecture video. So I don't think we have to actually go through that again. If you have any queries, then we can go through that. So now the problem from the original problem, the sub-problem is this. All you have to do is the same equation I have written, but then I have kind of written it in a different way. So this is this xk plus 1 is xk plus uk minus wk is just one kind of form, but in general that can be some function of xk, uk and wk. Again, this c of uk can in general be some function gk, like this entire term. Instead of here we have taken a linear form where r of xk plus c of uk, but in general it can be any function, some gk of xk, uk, wk and some fk of xk, uk, wk. So in general sense, so this is how you formulate the problem, where your j of xk will be given by this expression. So gk is my cost and this is my transition. And we are solving in the backward direction, start from n minus 1 and go to 0. Now for the very simple case where we assume the transition to be linear, such that xk plus 1 is ak times x plus a times x plus b times u plus w. And in that, and also the objective functions, the cost functions are also considered to be quadratic. So this is my r and this is my c. This is basically my r and this is basically my c. So this is the holding cost. So you can see the xk times q. So this basically tells me if you increase xk, this particular cost will increase. So this will kind of force me to have as minimum inventory as possible. And this is my uk is basically c times the cost. So this basically tells me that you have to purchase as minimum as possible so that you can meet your demand. And this is the residual cost. At nth step, I cannot do anything further. So this is the residual cost I'm going to have. And if I can minimize this, find a policy pi such that I will minimize this particular quantity, then my problem is solved. You can also think of this is the same thing used in something called linear quadratic regulator in a control applications. You can think of this from a control point of view. You can also think of this as xk is the state that you are trying to maintain. For example, you have a remote control car, for example. In a remote control car, all you have to do is say it's an automatic one, like it automatically avoids obstacles and all that stuff. For example, you can think of it as a drone or something, where xk is a state basically given by the height that it is traveling, the speed it is traveling, and all those things will be there in xk. And uk are basically my actuator commands that I have to give. For example, how much speed the motor should rotate, the blade should rotate, how much speed the blade should rotate, which will indirectly determine what is the speed of motor that you have to use and which direction you have to turn, and things like that will come into this uk. So all we have to do is whatever excitation that we are giving, uk is basically the excitation, the inputs that we are giving to the motor should be as minimal as possible. I should not spend too much energy to move from one direction to the other, and at the same time I also need to maintain my state at a given level, and this will tell me how much weightage I have to give for each possible stage. So that again, how do we get those matrices and something is completely out of the scope of this particular course. But then the idea is we need to maintain the state at a given set point. So this xk will tell me for example, if you want to maintain the height at a say 5 meter or something, the difference from 5 and the actual height is what that will go in here, and which will tell you that if the difference is beyond whatever it has to be, how much weight is how much am I going to lose. So there could be multiple things that you have to maintain. For example, you can also think of a very simple thing like a room control. In your room, you have to maintain the temperature and humidity. Your AC tries to maintain temperature and humidity. So sometimes temperature is more critical than humidity. So even if the humidity is not maintained, you're okay with maintaining an accurate temperature at around some particular set point. So those kind of weightages, how much weightage to give for temperature, how much weightage to give for humidity is something that is captured in this Q. So that is basically my that will essentially determine how much energy I'm spending. So for example, if you want to maintain temperature, I have to spend 100 joules of energy. If you want to maintain humidity, I have to spend 50 joules. Then that information will actually be captured in this Q. And this R case, basically the excitation is based in terms of, for example, the compressor energy that I have to spend for maintaining temperature. For example, if T and humidity are two parameters, then the amount of energy I have to spend for maintaining this T will actually come in this R, and to maintain this P will also come in R. But uh, this is the compressor electricity that you're consuming, and this is the, for example, in terms of your comfort requirements or the total electricity bill or something, the in kind of rupees or something, for example, that will come into this Q, so that you will minimize the total cost as well as you will also minimize the amount of actions that you are taking. That is from a control point of view. The same thing even in the inventory control problem. In inventory control problem, X case basically tells you have to minimize the inventory, and this will tell you that you also have to minimize the purchasing cost. The derivation has been there in lecture videos, but all that matters for us now is once we solve these equations, we use this particular recursion formula that we have shown before, use this recursion formula, and then we solve for this, and this is the final optimal equations that I've get. What we have to do is start from this equation, you take Kn to be Qn, and then I should have written it in the same order, but you start from this equation, and then you update your K at any given time using this particular transition equation. And once you get the K value, you can substitute that in this equation and get LK, and from LK you can actually determine what is the value of UK star. Once you have all these values, you can directly calculate what is the total cost depending on your initial condition as this. So the extra term that I'm writing here is this is basically the variance of WK. So as I said, like WK is not known before, it is only given as a random variable. So it can you calculate the standard deviation of the random variable based on the historical data. So for example, if you have a new shop in some area, then you kind of see what are the demands. So for example, if you are going to a new place, and I don't know if you can relate to it, but if you are I don't know, since you are not a shopkeeper, you may not relate to it, but if you decide how much order you are going to have in a new place, if you set up a shop in a new place, all you can do is gather data in that place and see how often people will buy things. You take, say, last 2-3 months data, and from there you calculate the variance, and that is what will come here, and that will decide what is upfront cost that you have to spend. We'll just solve a couple of problems on this using Riccati equation to solve these optimal values. Then I think it will become more clear. Okay, are there any questions up until now? Yes. Yeah, I can hear you. C is you're asking about this UK transpose RK UK. So these are my control actions. Yeah, these are my control actions. For example, yeah, if you have your AC, when your AC, say for example, you take you will be controlling the valve, right? Like the throttle valve or something that will decide how much you are going to have. So how to control that? That is my control action that is going. So this is that UK. So I should not open too much. Or you can also think of this another example. For example, if you have a car or some, yeah, automatically, yeah, car would be a better example. So if you are moving in a car, and say for example you want to maintain your velocity, irrespective of, for example, your there is this cruise mode in these cars where your speed will be maintained constant, like if on some highways where you set say speed around 60-70 and it will be maintained always irrespective of whatever the road conditions are. You can go slope, you can go down, but the speed will always be maintained constant. So this UK in that times will be like, how do you vary your throttle? You don't have to, you have to spend as minimum fuel as possible and still maintain your velocity. So your state variable will be velocity and UK is a throttle position. It's basically the residual cost. It basically Residual in the sense, so since our prediction horizon is only up to n steps, it's like I'm only doing from 0 to n minus 1. I'm not taking any decision at nth step. So I'll only get u0 and so on till un minus 1. I will not have un, which means if I'm not taking any decision at xn, I cannot comment anything about what energy I'm going to use or any other, I mean, what the control action I'm going to have here. So this term will just go vanish. So you are left with only this term in the first one. So I just took it just taken out of the summation, kept as a separate term. Okay. Nice. Then I have some quick problems. These are very simple problems. So I don't think they should take much time. So you can quickly see the problem and you can tell me the answers. So we can close this faster. These are very simple questions, but these are very similar to the assignment problems, so that it will help you solve your assignment questions. So the first one is consider the inventory control model that I have shown before. At any time given, the shopkeeper has a capacity of m units. So this is basically the limitation he is having in terms of the storage area he has. If the shopkeeper has xk units at the beginning of time period k, then this obviously means that if he already has xk, then he cannot take anything more than m minus k. Because if that happens, then it will exceed his storage capacity. So this is kind of a constraint, an inequality constraint that we are having, that xk at any point of time should always be less than or equal to m. This is a constraint that we are getting from this. If m is given as 10, what are the possible values that xk can take? Like just as I said, so what it means is we are saying m equal to 10. So xk should be less than or equal to 10. So there are only three conditions here. It's a very simple problem. But the main point here is yeah, yeah. So the only point that I want to highlight here is you can formulate it as a constraint. Just as long as you know how to formulate it mathematically, then it is done. The next one is also a straightforward one, but here we are assuming that I've told like we are trying to minimize some r of xn plus the expected value summation of expected value of r of xk plus c of uk and something like this we have told, but then we didn't specify what this r and what this c are. I just told this is some holding cost, this is some purchasing cost. So here we are giving the specific values also. So I'm saying that r of xk is h times x of k, and the ordering cost is given by p times u of k. So this is a linear relation. So as long as my storage keeps increasing, then my cost for holding also increases proportionally. And how many units I will purchase, proportionally the cost is also going to increase for the purchasing. And if these are the values that are given, what is the cost for the time period k? This is also straightforward. So how do I calculate the total cost? It's basically my purchasing cost plus holding cost. That will be h times xk plus c times p times uk. Xk and uk are given, h and p are also given. This is a straightforward one, but often the problem is again these particular things are not actually linear. Say for example, you consider a different scenario for the one that we have discussed before. For example, you want to maintain the set point temperature, so your state is given by temperature value, and uk is basically the control action is say a valve position or something. Then the cost associated with maintaining the temperature at that given value is something that you cannot directly get. So how would you do in such scenarios? What would be this h of xk? What is the holding cost? So for example, if so for this is 27. So let's consider a scenario where my set point temperature is say 25 Celsius, and my current temperature is say 20 Celsius, or let's say current temperature is 20 Celsius. So this is my xk at the current time. So now I have to decide uk. Uk is basically my valve position. Let's say I denote my valve position with something. So at this particular point, UK is, we do not know, but it's something that we have to find. So how will I find? So like how will I minimize it such that I will have my objective is to maintain the set point temperature. So from 20, I have to go to 25. But the question is, how will I go to 25? So if I just plot it, so this is my K and this is my temperature. Say at K equal to 0, I am at 20. I know I have to go to 25. So what should be my control action? What should be my throttling position so that I'll reach 25? I can go to 25 in different ways. So I can go something like this. I can go something like this. I can go something like this. All these are possible ways. Depending on the value of UK I'm choosing, I can end up in any of the paths that I choose. So what determines which path I can take is my objective. So this is where the optimization thing comes always. So your kind of you always have a scenario where your number of equations are always less than the number of unknowns that you're going to have. So you need to have a goal or an objective that will decide which of these is the better one. So our objective should then say what is the cost associated with maintaining the given temperature and what is the cost associated with the changing this throttling position. So for example, if I maintain at 20 degrees Celsius, what is the cost I'm going to incur? Is if T is 20 degrees Celsius, then the air temperature is 20 degrees Celsius, then my compressor has to, the evaporator has to have more load, than the compressor load will increase. That will increase the energy consumption. So somehow I have to relate this T using some equation to tell me that this is the amount of energy I'm spending at 20 degrees Celsius. So for example, if I have a plot that says like this is a compressor power versus this is the temperature I am maintaining. So if as the temperature decreases, maybe compressor power is higher. So I'll have a plot like this that says that okay, between this temperature and this temperature, as your temperature keeps increasing, the amount of power that you have to consume is reducing. So I have to pick the corresponding one that minimizes work, and at the same time, I also have to spend a lower energy on on UK as well. I'll also have a scenario with UK. I'll have a different cost. So depending on the valve position, again, my consumption can be different. If I open the valve more, then there will be more mass for it and your compressor work will also increase. So it will have a different plot, something like this. So both of these will contradict. So eventually you have to have, this is where the trade-off comes. So optimization is all about dealing with these trade-offs. So now is where your engineering thing comes into picture. You have to give the weightage. That is where the Q and the other things comes. That is basically my H and P here. So these values of H and P will tell me how much weightage I have to give for XK and how much weightage I have to give for UK. So by changing a unit value of temperature, how much this is going to decrease, and how by increasing this, how much I'm going to decrease, so that eventually I'll have to have a trade-off between both of them. Depending on these H and P values, I can maybe at some particular combination of H and P, I will end up at this particular point. Maybe if I change the combination, maybe I'll draw both of them in the same plot. Like if I want to combine both of these, then it will be like your plot, depending on the weightages you are going to give, you can have different scenarios. You can have something like this where optimal happens at a particular combination of T comma U at some particular weightages of T and U. If you use a different weightage, then you might end up in a different value. Like depending on the weightages you are going to do, you are going to end up at different scenarios. So this will be for one weightage, this will be for another weightage, this will be for another weightage. You can also recollect this in terms of your PID control if you are familiar with PID control, where you change your KP, KI, KD values accordingly to get to set these values to match your demand. But there we do not have an objective as such, but here we are specifying these objectives. Is this example clear? Clear? Okay. Okay. This is another one. It's the same thing. Again, the inventory control problem. The storage units are 10, and I know the current value is 4. What are the possible values of UK? So this is the maximum value I can take, and this is the current value. What are the possible number of units that I have to order? What are the possible control actions that you have to take? You know, xk is going to be, should always be less than or equal to m. At the same time, xk plus 1 should also be less than or equal to m. And xk plus 1 is given by xk plus uk minus wk less than or equal to m. So xk is given as 4. So uk minus wk is less than or equal to 10. Sorry. Now you see that again the challenge comes here. We do not know what is the value of W, and exactly why we are saying the possible values for UK. If I know W exactly, even then I can have different values of UK, and that's where the optimization thing comes. So what we are trying to do is we have to find a U that will minimize the total purchasing cost. So if I have to minimize the purchasing cost, then UK has to be less than or equal to 6. So I can always choose UK equal to 0. Like I know it has to be greater than 0. Have to purchase something or do not purchase anything at all, but it cannot be negative. So it should be positive and it should be less than or equal to 6 plus WK. And so it means I can always, to minimize the cost, I can always choose UK equal to 0. But then the challenge is if I choose UK equal to 0, then I'm not going to get any XK plus 1. I mean, XK plus 1, if this is equal to 0, if the demand increases beyond this, then this term, particular term will go to 0 and it can actually go negative as well depending on the value of WK, so which means I will not be meeting the demand. That is something that we do not want. So you can always choose the 6 also, but again the problem comes here is we do not know the actual value of WK. That's why we are saying what are the different possible values of UK you can choose. So based on this, what are the values you can choose? It cannot be 8 for sure because UK has to be less than or equal to 6 plus something. So since it has to be less than, I can choose these values. You can say why can't I choose 8, because again, if you apply the same concept of random numbers, so if you apply expectation on both sides, since WK is a random variable, UK is going to be a random variable. So the expected value of UK is something that is going to be less than or equal to 6 plus expected value of WK, and this expected value of WK is 0. Is a basic assumption that we have started out with. So now imagine a scenario where you are trying to model some process where your noise is, you can always adjust your data set so that your expected value is 0. So essentially you take a mean and then subtract the mean out so that this particular assumption is always held true. So for example, if you are trying to model the demand for some quantity and it happens to be something like this, it has some trend in it. So for example, it has a weekly trend in it, say the sales of ice cream or something, which increases only on the weekends. So these are some weekends and the remaining periods it will usually be lower or something like this. Then the mean value here is not 0, it is some positive value. So if you take an expected value of this thing, then it is not going to be 0. All you have to do is take the data, subtract the mean from the entire data set, and then use that thing as your demand. So that constant has to be accounted for everywhere else. These are kind of a small tricks that you will anyways do. So is this clear? Yeah, if something is not clear, I think yeah, feel free to unmute yourself. Yeah. This is a main problem that we have addressed using dynamic optimization. So we are saying we cannot directly solve for the action, so we are trying to solve for some policy function in UK, which is a function mapping from SK to UK, where SK is the possible values of states and UK is the possible values of actions that I can take for every possible combination of states. So if mod SK is basically the number of elements in set, number of possible states is 5, and so essentially I have 5 possible states and I have 2 actions that I have to take. So now the question is, how do I find this mu k? So mu k is basically a function that tells that if I am in this state, I have to choose this particular action. So how many possible combinations will exist? So how do you say that it is 5 power 2? So you're saying I need to find mu k of xk is uk. So this is my mapping. Yeah. So you're saying 5 power how? So for every possible state, you're saying there could be 2 actions. Okay. So how do I put it? Okay, let's say this thing. So you are at this particular state. You can take any of these two actions. But the way I have defined this function uk is uk is actually a function of uk of xk. So which means I think, okay, I should have drawn it reverse, then you would have reversed your answer. So you see every possible value of, so should be the other way. Let's say if I put it on this side, then what would happen? This is how we are defining, right? This is my input. And this is my output. Sorry, this is my output and this is my input. So for every value of UK that I have to get, I have to try all the different possible combinations of xk. So so to put it in words, so for example, if you are at state 0, for example, if you are at this state, you have to take certain action. If how do I put it simply? Okay. Think I do not have a very good example here, but you can think of this in a different scenario where, for example, the case of AC that I have told before. So the temperature of AC can be in two to three different states, and at each for every possible state, you have different values of throttle positions. Now the question is that what we are trying to find is this mu k, which says that if I am at this particular state, what are the actions I should be taking? So for every action, for example, I can take the throttle position of 10% in all the possible values of states. So even at 20 degrees Celsius I can take, even at 30 degrees Celsius I can take, even at 25, even at 24, whatever be the temperature, I can take this throttle position. Similarly, I can take a throttle position of 0.2, again associated with all the values of xk I'm going to have, right? I don't know if I made sense. So basically you can have u0 as a function of x0, x1, and whatever states you have, whatever number of states that I have here, all of them. And again, u1 is also going to be something similar. This is one way of seeing it. And the other way of seeing it is x0. At x0, I can take u0, u1, whatever. So one or two, which one you think we are doing here? So this is based in the first way of formulation. What we are trying to do is we are trying to write u as a function of x. For every possible combination of x, I am trying to get a value of u. In the second case, for every possible value of u, I am trying to get a value of x. So what we are trying to do is find this particular formulation. So we are trying to get u as a function of x. So which means every value of u will have whatever number of combinations of x that I'm going to have. So for example, for one u, I'll have all these combinations. So for the second one, again, I'll have, again for this particular u. So this goes as, all of them have, so u1 has 5 possible combinations, and u0, this is basically u0 has u has 2 combinations, and that first u has 5 different possible values of x, the second u has 5 different possible values of x. This is one way of saying it. The other way, if you see, is you have 5 different states. Each value of state has 2 different actions that you have to take. I think you got confused between this and this. So which one do you think we are doing here? I'll just remove the unnecessary ones. So which one do you think we are doing here? I have 2 different actions that I have to take, and there are 5 different states. So every action has 5 different possibilities. This is one kind of formulating the problem. The other one is this, where I have 5 different states, and each state has 2 possible actions that I can take. So one or two, which one we are doing here? Second one. So this will give you 5 square, and this will give you 2 power 5. And we are doing the second one. This is 32. I think now it is clear. Now it's the same thing, but a slightly different one. The previous problem, what we have done is we have asked you what is the number of decision rules at time period k. But now the question says that you have to do it for n equal to 2, two different time steps. So now I have the same problem. So I have 5 different states, and each state I have to take 2 different actions, and like this I have to do 2 times. So the number of combinations will be 2 power 5 whole square, right? And whatever number it is it 1024, I guess. I think this is clear. If the previous one is clear, this should be clear. All we have to do is just multiply again with another time set. That's it. But you can see the challenge here. So now we have to evaluate 1024 combinations of to determine what is optimal value. So this is where optimization is kind of useful. So you know that the problem is solvable, you know there is a solution, but then you cannot go through all possible states. Now, if you see this in this way, I clearly told you that mod sk is 5 and uk is 2, which means I have discretized my domain into saying that I can only have 5 different possible values of s, or sorry, 5 different possible values of states and 2 different possible control actions. But in reality, imagine a scenario where you have a very precise control, some space application or something where you have a very precise control, and this UK will be in some very high number, say 100 or whatever levels you have. So you can control, for example, in the throttle valve, you can control let's say 10 levels or 15 levels, depending on the precision you have, depending on the application you have. The number of levels of control that you can have in UK can be very high, and the number of possible states can be actually even more higher. So the number of values of temperature can be anywhere between 20 to 30, all real numbers between 20 to 30. You can discretize it at whatever level or whatever accuracy you want. That this can easily go up in hundreds or even thousands, and this can also go up in hundreds or thousands. So you can see the challenge is now then I have to evaluate the possibilities, for example, some 100 power 1000 possibilities. And I cannot go through all such combinations to determine what is optimal point. And that is exactly where all these equations and all these introductions are useful. It's just to kind of you can appreciate what the problem is and how these techniques are actually helpful. Nothing more than that. Okay, now I've taken a set of DP equations. So I'm telling you that the residual cost is 0, which means that at any other step I do not have a residual cost. All I have to do is minimize the total expected cost. This is my holding, this is my purchasing cost at that particular step, and once I use this particular step, I'll go to the next step and I have to minimize the cost at the next step as well. So instead of the entire summation thing, I've just put jk plus 1 of this particular term. Now what we are saying is where this denotes inventory at the beginning of time period k plus 1 for given values of this. Fk depends on k through xk, uk, wk. So this fk, whatever we are putting here for an inventory control problem, this statement tells you that this fk is independent of k. So the function, so this fk is basically xk plus 1 is some function of previous state. So what this question asks you is this fk independent of k? To put it in words, what we are trying to ask is, what I'm trying to ask here is this transition, like from a given state to the next state, something that is going to change with time or not? So the value of this function is going to change with respect to time. But what about the functional form? So in the inventory control problem, what is fk? In the inventory control problem, our fk of this is basically take the first 2 arguments, sum them, and remove the demand term. So this is how we define. So my fk is, this is my first argument, this is my second, and this is my third argument. You have to sum the first 2 and then remove the third one. That is how I define my fk. And this particular functional form is kind of same across all the iterations. That is not changing with respect to your iteration. This is like the only thing that is changing is the actual values of xk, uk, and wk, but the functional form itself is independent of f of xk. So what I mean, for example, it's for example at f0 is say x0 plus u0 minus w0, and if f1 is x1 minus u1 plus w1, something like this, then it means that the functional form itself is changing. In that particular scenario, you can say that fk is not f, is kind of dependent on k. But in the particular problem that we have considered in the inventory case, that is not the case. At every iteration, at every step k, these values are the same. I mean, the functional form is the same. The actual values can be different, but the functional form is the same. So fk is actually independent of k. Is that clear? Okay. Okay. Can you tell an example where fk can actually be a function of k? And like, can you come up with an example where that will actually be a function of k? It doesn't have to be inventory or anything. Any example that you can think of. So fk, what does fk represent physically? Yeah, so fk is basically my transition dynamic. Yeah, so it basically is the transition. Yeah, it's basically the dynamic equation you are saying. So this is some transition dynamic equation. So that is not going to change is what you're saying, right? So like, are there any examples where it can actually change? Maybe you can think of it. If you have some, you can maybe by end of the class, if you come up with any, you can just text them. Yeah. The next one is the same problem in the previous case. J naught of 3. So this is more of a notational point of view, just to be sure that you understood the notation. So J naught of 3 is the quantity ordered at time period k, which minimizes the expected total cost when the inventory at the beginning of time period 0 is 3. Is this statement true? What is the meaning of J0 of 3? The notation I have been using is J represents the cost. So J0 of 3 is the cost that I would be incurring at the initial step, where 3 is basically my x0. X0 is my initial stock, the stock at t equal to 0, at k equal to 0. So what this particular statement says is it's saying the quantity ordered at time period k, which is uh, not true. This is false. But if I want to say what is the quantity ordered at k, then that is basically u3. The quantity ordered at some particular time is basically u3. This is more of a notation, so I don't want to spend more time on that. Okay. Now we will solve. Okay, before even solving, this is standard formulation that we are taking. I just replace the plus with minus. Let's say it is a zero mean thing, so plus or minus it is not going to affect that much. Uh, Assume that this is a zero mean and then it has a finite variance. The optimal control policy is given by this particular expression. So the question now is the optimal control policy, whatever this is at any time k is linear in xk. Is this statement true or false? Seems true. Okay, why do you think it is true? Okay, that will always be zero. Like for all the problems, we have taken this to be zero. Like if this is also kind of, if this is not true, if the variance is not a finite thing, then there is no way you are going to get any solution. So these are kind of true for all our problems. So this has something to do with this term, the cost that we are trying to minimize. So what do you notice in this cost term? Yes, it is quadratic. So this is the quadratic, and then your transition dynamics is linear in nature. When your transition is linear and this is quadratic, then we have the Riccati equation that I have shown some time back. So in the Riccati equation, you know that uk at any optimal step is basically some linear operator times xk, right? this is a linear operation. So that is why we are saying the optimal control policy is linear. So it's only a special case that you have, that because the transition is linear and you have a quadratic cost term, this is going to be true. It has nothing to do with this. Okay. It's the same problem as before, so you can just quickly solve it. The same transition dynamics, but then I'm telling you that at n minus 1, this is the particular state value. What is the optimal control at n minus 1? So I'm asking you, what is un minus 1 value? How do you solve it? Let's say you do not know anything about Riccati equation or anything of that sort. What will you be doing? So let's say we just start normally. So what we are trying to do is minimize this particular cost. So how will you start out with saying, say, xn is basically xn minus 1 plus un minus 1 plus some wn minus 1. That will give me xn. And for example, I know the xn minus 1 value is 2 plus, let's say this is u, plus some random noise that is added with some zero mean or something. Let's say that is w. This is my xn. So what we are trying to do is minimize this particular cost. So what am I trying to minimize is f equals to xn square plus, I just have one step, so I'm just taking xn minus 1 square plus u square. This is what I'm trying to minimize. So all we have to do is equal to 0 and then find the corresponding value of u, right? Like this is how we started out with. Like if you are not into dynamic programming or anything, then this is what we are trying to do. So we have to find that particular u that will minimize this entire thing. So can you solve it? Can you quickly solve this? This is just a quadratic. Okay. It goes something like this. So this is some random thing. So this is a random variable. So if you just take expected value of u, so it will be minus 1 plus expected value of w, I have already told to be 0. So this is going to be minus 1. If you don't know anything about Riccati equation or anything, since this is a single step, this is very straightforward. Now you can see the complexity that you're going to get when you have more number of steps. So instead of doing all of that, he has already derived it. So we can directly use the equation. If you want to use the Riccati equation, so what were the terms that I have told before is we start with determining the values of k. So kn you can take it as qn. In this particular case, if you compare this with our standard equation, so this will be something like xk transpose qk times xk. So the value of q, since this is xk square, the qk is 1. This is 1. And then we have an equation that relates with kn minus 1. We have a relation between kn minus 1 and kn. So this is a relation between kk and kk plus 1. So if you were to substitute these terms, you can compare this. AK is basically 1 in our inventory control problem. Bk is 1. So if you take A and B as 1, so A is 1, B is 1, so all these terms will actually go off. So all that you have here is kk plus 1 minus, if I were to simplify it from this equation, so I have kn minus 1 is ak is 1, so that is kn minus kn times kn square by kn plus r is also 1. So in our case, q and r both are 1, which is 1 plus 1. So this turns out to be kn times by kn plus 1 plus 1. So I'll just take the direct equation. So I have 2 times kn plus 1 by kn plus 1 is 1. So I have kn minus 1. And once I have kn minus 1, from there I have to determine the value of Lk. So Lk is basically Ln minus 1. I know the value of B and all of that, so I can directly substitute the values. This is kn minus 1 plus 1 whole inverse. So I'll just write it as kn by kn minus 1. Sorry, Ln minus 1 is kn by kn plus 1 times your 1. This is what I have. So I don't even actually need the value of kn minus 1. Should have skipped that part. Okay. I can directly use k and get the ln minus 1 value. So this will give me minus half. And from there, I can directly determine what is optimal value at n minus 1. It's basically ln minus 1 times whatever xn minus 1 value you are going to have. So that is minus half times 2. It's like it just now becomes an iterative equation. So you have to start with some k, you have to use qn, get kn, from there get ln, determine the optimal value. And once you have this, you again go to use kn, get kn minus 1. And if you know xn minus kn minus 1, you get un minus 2. And once you have xn minus 2, you get, so you can keep doing that iteratively. So all the problem is now just become a recursive one. So instead of doing all these things, for single step it is easy. Now if you have more steps, then you have to add those terms as well, and this term keeps increasing in solving this. You can solve this, but then it will become a little more complicated. So this would be a simple way. It's again for a special case where you have a linear transition dynamics and also you have quadratic cost functions. I hope this is clear. This is just another extension of the same problem, but then I have estimated for 2 origins instead of a single time step. You just solve it for 2 steps. So you start with x0 equals to 2. You have to find x1, and then you have to go to x2. So the optimal control to apply at time t equal to 0. So you have to find u0. U0 is the question. U1, and this is a final time step, so you don't have u2. Again, as told, in the last step, you don't have any control action. Only in the last step, all you do is stop with whatever you have. So this is the dynamics. So how do you solve it? Again, you start with the Riccati equation and you will be able to solve. Just now we have written the equation. So we have kn equals to qn, which is 1 in this case, and kn minus 1 is 2kn plus 1, kn plus 1. I hope this is correct. If I have done anything mistake, please let me know. So just substitute it. So this will be 3 by 2. Once I have kn, from this I can calculate ln minus 1 as the equation I have, minus kn by 1 plus kn minus half. This implies un minus 1 star is going to be minus half times xn minus 1. It's n equal to 2, so that is basically x1. I do not know x1 value as of now, but let it be. So kn minus 1, and from this I can calculate ln minus 1 is minus kn minus 1 by 1 plus kn minus 1. This is 2 by 1 plus 3 by 2. This is minus 0.6. So once I have ln minus 1, sorry, this is ln minus 2. This implies un minus 2, that is u0. Ln minus 2 is minus 0.6 times x0. X0 is given as 2, which is minus 1.2. So at t equal to 0, I have to have a control velocity of minus 1.2. Now what is the control action at u1? I do not know x1 as of now, but how will I know x1? X1 is basically x0 is basically 2 plus I know what is the control action I am taking. I'll just write the equation first. So you have x0 value, you know the control action you are taking. Now once the demand realizes, once you know the actual value of wk, you will substitute the wk, then get the value of x1, and from there you will calculate the value of u1. Now you can see the advantage using the policy function. So once you know the policy function, you do not know the value of u1 directly, but you know what to do once the actual value of x1 is realized. Once you know the value of x1, then you can actually use the policy function to determine what the control action you have to take. So that is the main advantage that we are saying that we'll solve using these policy functions. Hope this is clear. There are no questions in this. Okay. So this is the last problem where you have the same equation, same set of problem, but then the only question that we are trying to ask is, instead of solving for the optimal control action, the question asks you to find the what is the optimal cost if the system starts at x not equal to 2. So essentially this is my J0 of x0. This is what I'm trying to find. This is again a straightforward thing. So I've already written down, like you can go through the derivation later. So we know the equation for this goes something like the initial value of k times instead of quadratic function, so x0 square, plus you have it's a two-step process. So you'll also have to take k1 times whatever variance you're going to have. This is what we have. This is the initial cost associated with it. So this is the variance term that is going to come up with. As I said, like the moment variance becomes infinite, then there is no point of doing any optimization whatsoever, because once it goes to infinite, then your cost is going to infinite. That is not a feasible problem. So we need to have a finite variance. That's how we started always with. So in this case, we know the values of k1, k2. I've just calculated it before. So I know k1 as 3 by 2, and k0 as k2 is 1, k1 is 3 by 2, and k0 is something I haven't calculated. Okay, k0 is going to be 2 times k1 plus 1 by k1 plus 1, 2 times 4 by I have k0, I have k1. All I have to do is substitute it in the equation. So I have j0 of x0 as k0 times x0 square plus k1 times, so 0.4 plus 3. I think I messed up some calculation. Oh, sorry, there is 2, n equal to 2, so there is another term that is coming, k2 times expected value. So, and I know the value of k2 as well. K2 is 1. If I substitute that, did I do some mistake somewhere? This is 6.4. I'm getting something like 11.4 or something. I think I might have missed something. Check the calculation means. K2 is 1, K1 is 3 by 2, and K0 is 1.5 plus 1, 0 to 2.5, 1.6. So this is also correct. I think I might have done some mistake over here. You can also quickly check it, but the idea is the same. So you have an initial cost associated with it with respect to x0 step, and for all other steps, whatever is your variance, that is going to increase your cost. So to put it intuitively, if you want to understand, this variance will kind of tell you how uncertain you are about the demand that you're going to have. The more uncertain you are, the more cost you're going to incur. So it's like if you know that you're not going to have, say for example, the petrol price is going to increase tomorrow, and you do not know how much it is going to increase, then you're going to stock it up, whatever it is item. Say like during the COVID, and you know that some demand is going to increase, and you do not. The more uncertain you are about the demand, the more stocking up you're going to do. So that is exactly what is reflected in this. So as your variance keeps increasing, your uncertainty is going to increase, and that means your J naught is the initial cost that you're going to, the optimal cost that you have to do is also increasing. That is the intuitive thing. So I'll just go through the calculation again, and then I'll update in the final thing. But if you see anything wrong here, let me know. Maybe in the equation you might have done some mistake. Let me just quickly check. So kk is basically k1 is basically 1 times k2 minus k2 square, the 1 plus k2 plus 1, k2 by 1 plus k2 plus 1, 1 plus 2 k2, 1 plus k2. So this is correct. The equation for k is correct. This is also correct. Maybe I have given some error in this options. Okay, I'll check this calculation part, but is this clear up until here? Then this is the last question I have. But do you have any other queries? I have. I don't think if you have received any mail regarding an extra class or something, right? Yeah, I've actually sent a mail to NPTEL. I don't know if you have actually received it. They actually not sent anything, any update on that. Maybe they'll send sometime. Yeah, I think they sent a mail just now. Yeah, they sent a mail at 5:45. Yeah, they sent a mail. Tomorrow there is one more session. You will have received now. So like 10, 15 minutes back they sent it. So, so what I'm planning for tomorrow is I have some problems, some example problems that I've taken from another course on one on KKT conditions and some problems on linear programming. All of one on nonlinear problem, one on linear problem. So one on heat transfer and the other one's on general inventory management kind of stuff. If you're into OR, so I have already actually I kept the last week not for the exams because we haven't discussed like all the assignment problems I have discussed are only for assignments, so they are not any problems that you actually use in real world. So most of them are theoretical. So I thought, okay, the last week I'll only teach some problems where you actually solve them instead of this multiple choice kind of thing. Okay, regarding an exam point of view, it's always your assignment problems. It's only multiple choice. Whatever you have in your assignments, you're going to have very similar questions. I think around 60 to 70% will actually be the same questions, and the remaining some new questions. But most of it will be assignment based. It's not going to be tougher than whatever your assignments are. I've taken whatever questions I have discussed in this are also mostly most of them are from the last year assignment questions. So if you can go through this and that, it should be sufficient for your exam preparation, I guess. Right. So tomorrow's problem, yeah. Sorry. No, these questions are not from that point of view, but these are the questions I have taken from most of the questions are taken from your last week course assignments. The questions that I'm discussing here, most of these are from the last year, the same course in the last year assignment problems, which are more or less similar to your this year assignment questions as well. So it will be more or less, your exam will also be more or less the same. So if you're good with the assignment questions, then that should be fine. I've taken some extra questions also, but then it doesn't matter. Your assignment questions are your base. Fine. Yeah, if you have no further questions, then I think, yeah, tomorrow it's up to you if you want to join. So the questions that I'm planning to, okay, I'll quickly show you if you want. One second. Yeah, so can you see my screen? Okay, I don't think you are. I'm just sharing my screen. Can you see my screen? I have some problems. So these are linear programming problems, but these are more on solving them. Like in whatever assignments that we have, all of these questions are basically on how to formulate the problem, and I have left it at that. I haven't discussed how to actually solve them. I told you, okay, it's the word problem, then how do you convert it into math? That is the only thing that we have discussed during all the sessions till now. I haven't actually solved a problem. So tomorrow I thought, okay, maybe we'll take some problems and then actually solve them. So this is one problem. This is also something that you can formulate it pretty quickly. But then how do you solve it? Okay, I have this equation. I want to maximize this by given this constraints. So how do I solve it? Whatever we have discussed using the methods like Kuntikar conditions, KKT conditions is something that we have discussed. How do you use it? Lagrange multiplier, how do we use it? How do we use these methods to actually solve this problem? So this is one thing. And then I have another problem is also very similar one. You have the same set of equations, but then you have more number of equations. So this is just how do you write the KKT conditions. So this you can solve using linear programming method. This is a linear programming problem. You can also solve it using KKT conditions. So how do you solve it using KKT conditions? And then I've taken a non-linear problem also. Like you have some non-linear problem like this that you have to maximize something subjected to equality as well as inequality constraints. Then how do you formulate it and how do you solve it? That is one more problem. And the last problem is on heat transfer. So you have some nonlinear function, you have some heat transfer coefficient, and you have some diameter. All you need to solve is for what should be the values of this theta and d such that you have whatever your objective is. This also formulating a problem is a straightforward thing, and how do you solve it using Lagrange multipliers? And what is the physical meaning of this? I have only these 4 problems that I want to discuss tomorrow. If you're interested, you can join. But these are nothing related to your actual exam. Like from point of view of an exam, you are not going to solve any of this. Right, then that's all I have for this week. And we'll meet tomorrow then around the same time, 5 to 7. Thank you.